Good morning and welcome to my today's lesson. Thank you so much for always making time for my lessons, and today I have something very important that I want to share in my today's lesson. And whatever I want to share today will actually center on carbon and its compounds. Carbon and its compounds, and this is a very important topic in as far as our Kenyan curriculum is concerned. It actually positions itself as the last topic in Form 2, and in this case I'm going to actually discuss this topic in detail. And what I want you to actually take note of is that first, carbon is actually an element that gets found in the periodic table, and this element is actually number 6 in as far as its position in the periodic table is concerned. And of course its electron configuration or electron arrangement, in that case the arrangement of electrons in the energy levels in as far as the structure of an atom is concerned, is 2 to 4. So in that case, or in that regard, I can actually be able to say that this element is found in group 4. Why? I've always been telling you that the group of an element, in as far as its position in the periodic table is concerned, will actually rely on the number of electrons in the outermost energy level. So there are 4 electrons in the outermost energy level, and that means this element is found in group 4. But now, in as far as getting the right answer is concerned, we always write the group of an element using what you call the Roman numbers. So I'll always say group 4. Correct. What about the period? This element should be found in period 2. In that case, it's actually period 2. Period is always written using numerals 1, 2, 3 going forward. So how many energy levels does it have? It has 1, 2. So the number of energy levels will tell us more about the period of that element in terms of where it is located in the periodic table. Having noted that, I also want you to note that if I look at carbon, I should be able to note that carbon is actually an element that can be able to get found in different forms. And these forms are, in other words, I'm trying to look at the sources of carbon. Where can I get this element? Number 1, carbon can actually be able to exist as free element, for example, or in free state. Good. Or it can also exist as an element but now in a combined state. Or it can also be able to exist in what we call crystalline forms. Very good. And lastly, we can say it exists as a component of carbon oxide. So those are the forms in which carbon can really be able to exist. And let me just begin with the first one, where carbon exists in a combined state. Then I can be able to go to how carbon can actually be able to exist in a free state. So if I look at how carbon exists in a combined state, I can say now which combined states will contain carbon. Good. which combined states will contain carbon. And in that case, we shall be able to mention one combined state such as sodium carbonate. And sodium carbonate is actually also referred to as soda ash, or others will call it washing soda. Great. And another form in which carbon can exist in as far as any combined state is concerned is sodium. You can see the carbon here. So in combined state, good. So you have sodium hydrogen carbonate. You have again the carbon here in combined state. So this one here can also be able to get called baking soda. Baking soda. In that case, or we can as well be able to call it sodium bicarbonate, or others will call it bicarbonate of soda. Good. So I have either baking soda, sodium bicarbonate, or bicarbonate of soda. Okay, I can also be able to talk about marble chips, which can also just mean calcium carbonate. Good. Marble chips, calcium carbonate. Or you can refer this as well to something referring itself to limestone, and limestone is also referred to as calcium carbonate. Limestone or calcium carbonate, marble chips or calcium carbonate, or chalk can as well be able to have the same chemical formula, which is calcium carbonate. These are the forms in which carbon exists in combined state, but there's many, and sometimes mentioning most of these compounds becomes so tiresome, so you can just pick a sample and be able to use that as a limelight for you to understand what you're supposed to actually have in as far as the forms in which carbon exists is concerned. So if you'll be looking at this topic called metals, you'll be able to actually understand that iron 3 carbonate can also be a source of what? Carbon. And some of these compounds are actually having what you call the names that they got actually from the people who actually discovered them, like siderite, ferrocite, siderite, chalcocite. So all these ones are actually names referring to compounds that can be ores or sources of very important elements like iron, zinc, lead, copper, and others. So all these compounds are actually very, very important. Look at malachite, also another very important source of carbon. Copper 2 hydroxide, copper 2 carbonate. We have what we call xerosite, also actually a source of carbon. So all these compounds are very important as far as the sources of carbon are concerned. And these are just some of the compounds you're supposed to capture as far as where carbon exists in combined state. So you have carbon here, we have carbon here, we have carbon here. So I've also mentioned about azurite, what we call malachite, you see, what we call siderite. So those are also sources of carbon, or the combined states of carbon. Okay, so maybe I can go to something else, and in this case I may mention the free state. The free states. Now, in which free state will carbon actually exist? And in this case, you may actually be able to mention very, very important states. And in this case, when I talk about free state, I'll be able to actually mention, for example, the crystalline forms of carbon. So one subcategory of a free state in which carbon exists is is actually the crystalline forms. So we have what you call the crystalline forms. The crystalline forms or the regular forms in which carbon can actually exist. For example, we have what you call diamond, we have what you call graphite. Good. Diamond and graphite. And if you mention that, then you are supposed to actually go to the non-crystalline. So what you call the non-crystalline. So we are done with the combined state. We have gone to the free state. You have said an important subcategory of the free state is the crystalline form. This crystalline form can be, for example, diamond and graphite. Then we can also mention the non-crystalline. So non-crystalline. And remember, this non-crystalline is also referred to as amorphous. Amorphous. So this is also a very important source of carbon. Amorphous. So this can actually just be able to mean the same thing. So you can either say non-crystalline or amorphous. Good. Amorphous forms of carbon. So non-crystalline or amorphous. Of course, chemistry and biology are actually science subjects. They demand that you actually use the right spelling. So there's an RPHOUS amorphous form. So which are these amorphous forms of carbon? We have examples that may include the following. Like we have coal, we have coke, we have peat. You see, these are just examples of what we call the non-crystalline, the irregular, the amorphous forms of carbon. So you have coal, coke, peat, we have charcoal. And this charcoal can either be from, for example, the wood charcoal or the animal charcoal. Good. Amorphous, non-crystalline or irregular forms of carbon. Coal, coke, peat, charcoal. It can be either wood charcoal or animal charcoal. See? So it is actually good that you actually understand these things in detail. You have what you call even soot. The soot is also sometimes referred to as the lamp black. The lamp black. I'll be able to explain this in detail. The one that actually gets deposited when fuels burn in inadequate supply of oxygen. See, so it actually forms what you call the lamp black. So coal, coke, charcoal. And these may also be able to get discussed here. And apart from the crystalline forms, the non-crystalline forms, there's also another form in which carbon can exist, and this form is called Fullerene. Fullerene. Fullerene is actually a source of carbon. It has 60 carbon atoms. It actually gets that point of being used in so many areas in as far as medical issues are concerned. So it's actually a source of carbon that has 60 carbon atoms in as far as its structure is concerned. So it has actually been widely used in different areas in as far as medical issues are concerned. Now let me just take you somewhere here. When we talk about diamond and graphite, it's good that you understand these things. In chemistry, we always say diamond and graphite are allotropes of carbon. The regular forms, the crystalline forms of carbon, diamond and graphite. Allotropes. Now you may want to know the meaning of allotropes or allotropy. Allotropes or allotropy. You see, look at this. Allotropes or allotropy. You see, allotropes are forms in which an element exists in the same physical state. You see, look at this. If I come here, I have allotropes of carbon as diamond and graphite. This is actually a shiny crystalline structure which is transparent. This is actually a black substance. You see, that is actually gray in appearance or black. If you look at diamond and graphite, they are all allotropes of carbon. Allotropes are forms of an element, you see, which are actually in the same physical state. For example, you see, these forms of these elements can have the same chemical properties, but their physical properties will gradually change. I want to repeat this. Allotropes are forms of the same element in the same physical state, for example, having the same chemical properties, but showing a gradual change in their physical properties, or showing differences in as far as their physical properties are concerned. Now, what is allotropy? Allotropy is actually an adjective. It tries to actually explain the existence of an element in different forms, in the same physical state, having the same chemical properties, but showing differences in as far as their physical properties are concerned. Let me give you a practical example. If I talk about a physical property like melting point and boiling point, look at this. Diamond is actually able to have even a higher melting point than graphite. That's a physical property. It's actually all about it being able to use all its 4 valence electrons in the bonding. So it ends up forming 4 strong covalent bonds that demand very high temperatures for them to get broken down. So that makes it to become a compound that has a very, very high melting point. Of course, there are those physical properties that are similar. For example, diamond is insoluble in water, graphite is insoluble in water, but they are soluble in polar solvents. So there are those physical properties which are different, and others are actually similar in as far as those allotropes of carbon are concerned. But just take note of this: the forms in which an element exists, for example, in the same physical state, having the same chemical properties. Why? Because they contain the same element, carbon. So they have the same chemical properties. But now they can show differences in as far as their physical properties are concerned. Now, if I'm done with that part, I can be able to actually come to something else. And this is looking at the last source of carbon. Carbon can be a component of carbon dioxide. Look at this. You see, carbon dioxide is actually a gas, also referred to as carbon 4 oxide, made up of 1 carbon and 2 oxygen atoms with what we call strong covalent bonds. This carbon has an average percentage of 0.03 as far as its composition in air is concerned. You can be able to see the carbon here. So this carbon 4 oxide or carbon dioxide forming 0.03% as its composition of air can also be a source of carbon in as far as whatever I'm trying to discuss is concerned. So you should be able to take note of that. Now let me just give you something in as far as this part is concerned. There's something you're supposed to note. What is this? Please take note of this. I want you to note that if I look at carbon and its electron configuration is 2 to 4, it becomes actually a point of discussion when I have to say that carbon has 4 valency electrons. You see, those are the electrons this element is going to use in as far as structure and bonding is concerned. So carbon will use all its 4 valence electrons. Now let me tell you one thing. There's a difference between valence and valency. Valence will refer to the outermost electrons in as far as the electron configuration of an element is actually concerned. But valency refers to the number of electrons an atom of an element is actually supposed to gain or lose for it to become stable. For example, if I say 2 to 6, you see, if this is an element which is obviously oxygen, because it's number 8, so it will be 2 plus 6, that is 8. I can say the valence of carbon is actually 6. That means the outermost number of electrons, the valence, the outermost number of electrons in an atom of an element in as far as its electron configuration is concerned. The outermost number of electrons. Valency, the number of electrons an atom of an element will lose or gain for it to become stable. So 2 to 6. How many electrons does it need to lose or gain for it to become stable? Look at this. If I write 1, 2, 3, 4, then I write 5, 6, 7, let me even say 8. I will draw a line through this point. So let me tell you one thing. Any element that has 1, 2, 3, and as far as the electrons are concerned, in its outermost energy level, it must be a metal. Look at that. And it must lose. And losing is actually positive. Any element that has 5, 6, 7, just forget about 8, because those with 8, if I say 2 to 8, this element is stable. The first energy level must have 2, the second energy level must have 8. So if an element has 8 electrons with outermost energy level, it does not need to lose or gain, so it is actually stable. This is a property for all the noble gases, the rare gases, the inert or the inactive or the group O elements. Why do we call them group O elements? Because they don't need to lose anything. So they lose nothing. So in that case, they will not lose or gain anything. So in that process, they are actually called group O noble or rare gases, like helium, neon, xenon, krypton, and of course radon. They're actually group 8 elements or group O elements. So I'll actually forget about this. So I'll actually mention about 5, 6, 7. So any that has 5, 6, 7 will be able to actually qualify to be a non-metal. In this case, it has to actually gain, and through gaining, it becomes negatively charged. So it forms what you call a cation. In this case, it is positively charged. It actually has to react by losing. Then it actually becomes an ion. If it has to actually lose, it becomes positively charged. If it actually to gain, it becomes negatively charged. So it becomes an ion. So metals are cations. They react by losing, they become positively charged. And metals are actually anions. They react by gaining, they become negatively charged. You're trying to imagine if an element has 6 electrons, for example, oxygen. So 6 is here. So it has to gain for it to become negatively charged. So it becomes a non-metal. So oxygen is a non-metal. So 2 to 6. So 6. The second energy level must have a minimum of 8, but this one has 6. So what happens? It has to gain 2. You see. So the number of electrons an element gains or loses to become stable is valency. So in this case, the valency of oxygen is 2. Why? These are the number of electrons it's supposed to actually gain for it to become stable. And I'm telling you, valency refers to whatever it has to gain or lose for it to become stable. And in this case, it's supposed to gain. So it gains 2. So its valency is 2. Okay, so carbon has to use all its 4 electrons in bonding. So it forms very strong covalent bonds. How many are they? The first covalent bond, the second, the third, the fourth. So what is a covalent bond? You may be wondering. A covalent bond is a bond that has to involve equal sharing of electrons. For example, carbon is combining with hydrogen, isn't it? Carbon is 2 to 4, hydrogen is 1. So in this case, I know very well that carbon requires 4 electrons for it to be stable. I've told you the second energy level must have 8. So this one has 4. So it has to actually have an extra 4 electrons. So, but hydrogen can only produce 1. So that means we need 1 carbon and 4 hydrogens. Why? Because carbon needs 4 electrons, but hydrogen can only contribute 1. So what happens? We have to have 4 hydrogen atoms, each contributing 1, for carbon to end up having 4 electrons getting added onto its electron configuration. So in this case, you'll have something of this sort. Remember, when you're looking at what you call structure and bonding, covalent bonds are shown using only the outermost electrons. So you don't have to consider these ones. You only use the outermost electrons. So this is the first hydrogen. It gives out 1 electron. This one gives also 1 electron. This one also gives 1 electron. This one also gives 1 electron. So if it gives 1 electron, as far as each hydrogen is concerned, to the carbon atoms, the carbon also contributes 1 electron in each case. You see? So in that case, this is the first covalent bond, the second covalent bond, the third covalent bond, the fourth covalent bond. What is a covalent bond? A bond between 2 nonmetals where there's equal sharing of electrons between those two nonmetals. And this is what we call methane, which is an alkane as far as organic chemistry 1 is concerned. So if I'm done with that part, let me just try to break down these allotropes of carbon, forms in which carbon exists in the same physical state. Now the solid state, for example, graphite and diamond, having the same chemical properties but showing differences in as far as their physical properties are concerned. Let me start with diamond. If you look at diamond, diamond is actually the purest form of naturally occurring carbon. The purest form of naturally occurring carbon. And if you look at this carbon, you'll be able to actually understand that it is actually able to have all its 4 electrons getting used in using the forms of carbon. The forms of carbon. For example, we are saying now diamond is an allotrope of carbon. Just like the way you can have, for example, phosphorus. Phosphorus is also allotropic. It also exists in different forms. For example, we have the red phosphorus and the white phosphorus. Look at that. If I also talk about another element like sulfur, sulfur is also allotropic. We have what we call the rhombic sulfur. We have what we call the monoclinic sulfur. See, we have what we call the colloidal sulfur, and even the plastic sulfur. So all these ones are actually allotropes of sulfur. So an element can exist in different forms, just like the way phosphorus exists as a red phosphorus or a white phosphorus. Sulfur exists as rhombic, monoclinic, colloidal, or plastic sulfur. So we have said carbon also is allotropic, having diamond and graphite. So I want to actually discuss more in as far as diamond is concerned, and I want to actually note or bring this to your attention that diamond is actually a highly crystalline and very purest form of carbon. It is actually colorless, so highly crystalline, colorless, and of course the purest form. So if you compare diamond and graphite, diamond seems to be the purest with a very small amount of impurities in it. And so that in case you may actually get asked to give the purest form of carbon, you have to mention diamond. So it is highly crystalline or very crystalline in nature, and it is non-amorphous. And that means in this case, you are supposed to actually make it again look so colorless and very purest. We have said we have what we call the amorphous carbon. Amorphous carbon is the forms of carbon with no shape, the non-crystalline. But the non-amorphous carbon or the crystalline carbon should have a shape which is regular. So this diamond is highly crystalline, it is colorless, it is actually purest form of carbon. And in this case, it is what we call a giant tetrahedral shape, because it's actually crystalline or non-amorphous. So it has what we call a giant tetrahedral shape. Let me just give you an example. We have said carbon is number 6, that is 2 to 4. So that means it has to use all these electrons as far as bonding is concerned. So if you look at diamond, it uses all its valence electrons in as far as structure and bonding is concerned. So you have to have the first one, the second one, the third one, the fourth one, and the fifth. So it forms what we call a tetrahedral shape. Tetrahedral shape. Good. It forms what we call a tetrahedral shape. Look at that. That's why we are saying it has a giant tetrahedral shape where all its valence electrons are used in structure and bonding. So it uses all its valence electrons in structure and bonding. So it exists as a regular array. If those atoms repetitively bond with each other, It exists as a regular array or a crystal lattice with quite a good number of atoms, or carbon atoms, getting bonded together with what you call the strong covalent bonds between them. So you can have a good number of these, again, bonding. You see, so the bonding goes on, and in that case, you may have what you call a regular array or what we call a crystal lattice made up of several carbon atoms bonded together by strong covalent bonds. So the repetitive aspect of the carbon atoms bonding together with strong covalent bonds makes diamond to have very important physical properties that I'm going to actually outline in my next discussion. So the physical properties of diamond. Number one, diamond is the hardest substance on earth. Why? All the carbon atoms in the structure of diamond are held together by strong covalent bonds in a regular manner, forming what you call a regular array or a regular crystal lattice. And in that case, it makes diamond to be the hardest ever existing natural substance on earth. Number two, I've said it has what you call a regular tetrahedron shape. You see. And apart from this, you should note that diamond has what you call a colorless appearance, a shiny colorless appearance, or a shiny colorless appearance in as far as the way it looks like. And in this case, you should also know that one, so I've said one, it is actually shiny, and of course it is actually colorless. Now why does it look shiny? You see, now looking shiny is actually also the same as having what you call a particular luster. You see, a particular appearance. Now it is actually shiny, or is actually colorless and very shiny, or have what you call a particular luster, because of what we call its high refractive index. So it has what we call a high refractive index. You see, it has what we call a high optical dispersion. So when light falls on it, the light has to actually get dispersed, so it looks so shiny. That's like the way new iron sheets look like. So it has what we call a high refractive index or a high optical dispersion. You see, so it becomes a very shiny substance, or a substance with a higher luster. Okay, so after I've mentioned, and of course the refractive index of diamond gets taken to be 2.43. If you compare this with that of water, which is actually 1.33, you see, like the way the physicians will say, a refractive index of a substance is equals to the velocity of light in the empty space over the velocity of light in a particular medium. That gives you the refractive index, the velocity of light in empty space over the velocity of light in a particular medium. That gives you the refractive index. Okay, and with that, you should also be able to know that diamond has what we call a high melting point and boiling point. Why? It's around 4,700 degrees Celsius. Try to look at that. Look at this. This is because in the structure of diamond, the carbon atoms are held together by strong covalent bonds. Those bonds require very high temperatures for them to get broken down, so that the carbon structure can get actually decomposed. So that means it has to have a high melting and boiling point. Something funny is that diamond is insoluble in water. Why? You see, diamond is actually non-polar, and yet, so diamond is non-polar, and yet water is polar. Water is polar to mean, when you look at the structure of water, water is polar because it is actually partially positive at one part and partially negative at the other part. So the two hydrogen atoms in water are partially positive, or are responsible for the partiality in terms of positivity in as far as this structure is concerned. Then the oxygen in the water is responsible for the negativity in as far as the structure of water is concerned. Why is oxygen negative? It tends to actually attract the bond electrons between the two atoms to itself strongly. So when it attracts all these two electrons, or the bond electrons to itself strongly, it becomes partially negative. leaving the hydrogen on this other side to become partially positive. So the same thing is actually also on this other side. The bond electrons between hydrogen and oxygen become strongly attracted to oxygen, making it to become partially negative. The other end made of hydrogen becomes partially positive. So oxygen becomes partially negative, the two hydrogen atoms become partially positive. Water becomes a polar solvent. A solvent which is partially positive at one end and partially negative on the other end. So non-polar substances cannot dissolve in polar substances. Look at that. Polar solvents can only dissolve non-ionic compounds. Look at this. If I have a polar solvent, for example, let me say I have water, which is partially positive and partially negative, and I have sodium chloride. You see, sodium chloride is actually a polar compound or substance. Remember, sodium is partially positive, the chloride part is partially negative. So the partially positive part of the water molecule will surround the partially negative part of the polar compound. Then the partially negative part of the polar solvent will surround the partially positive part of the polar substance, getting dissolved in the water. So the substance dissolves in the water. So that means if diamond is non-polar, it can dissolve in water, which is polar. So that means non-polar compounds can only dissolve in the non-polar solvents. Non-polar